Hello, this is Dr. Liu. In this video, I will introduce what potential energies mean. So we are already aware of kinetic energy. So that is energy associated with a moving object, something that has a velocity. So what about potential energy? This is something that has energy, but is not really associated with motion. So something that could potentially turn into motion. So let's think about a situation like this. So we'll have, let me just draw something here. Maybe a part of a table. So here's one leg, another leg. And on top of the table, you will have a coffee mug. Okay, so the coffee mug doesn't move. It just staying there statically. But what if you just gently nudge it over the edge? Well, it falls off, right? It falls off. Probably as it falls, it kind of turns a little bit if you just pushed it, right? So it drops to the floor. Probably get damaged, loses its handle or something, right? So the fact that you could make something move potentially is considered potential energy, and in this case, because the coffee mug is on the tabletop and it is potentially able to fall the whole height of the tabletop, that gives it a certain amount of potential energy. But if the coffee mug was not that high, say it's actually on a small stool, something like this. We have lots of step stools. We have a small child. He wants to reach things. So if the coffee mug were only here at this height, I'm pretty sure if someone nudges it, it falls off. Okay, it falls off backwards. I don't know how that happened. So then it would be a little less fast at the end. So this depends on, here is a useful factor is the height, right? This height here compared to this other height will determine how much kinetic energy the coffee mug ends up having. So yeah, the higher the height, the more gravity will accelerate it, right? The more gravity will accelerate it, the faster speed the object is at the end of that travel. So we classify potential energy in this situation as a gravitational potential energy because gravity would actually do the work to make the coffee mug accelerate to give it its kinetic energy. And the amount depends on number one, the height, number two, also the mass, right? Gravity is mass times g, so the force times the displacement, right? Here's the displacement, how much energy can be transferred. Okay, their displacement is this, and the force is mg. So this potential energy, EP, sometimes written as PE, just a play of words, potential energy, is mg, and let's call it a y because we like coordinates better than just heights. So we can always have this reference, a 0. So here's a y. So here's the y, maybe y2 of that coffee mug on the stool, step stool. This is y1 of the coffee mug on the tabletop. So this potential energy is proportional to mass because gravitational force is proportional to mass, and the potential energy is also proportional to the height because the amount of work that the gravitational force can do depends on how far you're falling, right? So the situation is like this. Here's gravity, it has a magnitude mg, and this is the whole displacement, right? This whole thing, I'm just drawing for the step stool. So that's the whole displacement. And these two multiply to each other with the cosine of a 0 degree, that's a 1. So that gives you directly mg over here and y over here. So this is the height is the earlier minus the later. So the earlier is y, later is a 0 and in our situation. right? So potential energy due to gravity. That is mg times y. So one thing we just noticed is the origin, the choice of origin, right? If you don't choose origin to be here, if you choose the origin to be on the surface of the step stool, then the potential energy values are all different, because then the height from this cup on the step stool will be 0. So this cup has 0 potential energy sitting on the step stool, and as it falls down to the ground, it will have a negative potential energy because the origin is here on the surface of the step stool. Now you're below that surface, right? So gravitational potential energy, again, it relies on a reference. It's just like kinetic energy, it relies on who's observing, right? If the object that is in question is observed by one observer, and then another observer may be moving relative to the first observer, that second observer will see a different velocity, right? So this is also true, except that now we're not talking about observers, we're talking about reference, the reference 0 or the origin. So you need to pick. If you are given an origin, then you just use that origin. Otherwise, you need to pick, you have to pick an origin and stick to it. And you need to be explicit with your choice, such as drawing this axis of putting a 0 where this height is, because if you don't, then next time you may think, oh, let's just use that as origin, and then once you change your origin, all the calculations may be invalid. And also, you probably haven't noticed is the potential energy itself, because the choice of origin is arbitrary. The potential energy value itself, it is not very meaningful. What is meaningful is the distance fallen, right? So if you fall from the tabletop to the ground, regardless of where your origin is, you have fallen a height of h. If you fall from this step stool to ground, your height changes h regardless where the origin is. So this tells us something about the potential energy due to gravity. Basically has much less meaning than the change of potential energy from one place to another place, two different heights. So the exact value, I would say exact, not PE due to gravity. Oops. Important. Then its change. Which is independent of origin. Whichever origin you choose, unless you somehow start pointing downward, that is not the choice of origin anymore. That also involves the choice of the axis. So this is the potential energy due to gravity. And we also have a second type of potential energy that is due to compressed springs. So this is just like the projectile motion lab we have. We fire projectiles using compressed springs. So now we have this situation. We'll have a spring. So we'll have this. Okay, sidewall to mount some springs. Okay, so here's my spring, and it has this fixed end on the left side. And now you have a movable end on the right side. So right now the spring is resting, and this is its natural length. So let's call it x0. Okay, so now we have x0. And if we stretch it, if we compress it, right, there will be a change. So let's try to stretch it first. Let's see, 1, 2, 3, 4, 5. So oops. Let's just make it that. Okay, I think I drew the same amount of turns or coils. Okay, so here's x1, here's x0. So the difference between the lengths, this is delta x. Say we can define this as positive for stretching. And the energy here, EP, potential energy due to a compressed spring, is it related to the spring's own property, K, which is a spring constant, and this delta x, but we square the delta x. So the K here, the K is called spring constant. The way it's typically given is in newtons per meter. What this means is you want to stretch a spring a meter longer than it wants to be. You have to apply K amount of newtons. So say K equals 10 newtons per meter, means to stretch spring so that you increase the length by a meter. That's really bad. We don't have very long springs to do that, but we can also proportionally reduce the stretch to require less force. So basically stretch the spring so that the delta x is equal to 1 meter. You need to apply 10 newtons of force. So that's what this K constant is. It tells you how stiff the spring is. The bigger the K, the stiffer it is, because you would require more force to stretch the same amount. And also you can proportionally go down. Say if you only applied 1 newton force, instead of stretching 1 meter, you stretch 1/10 of that, you just stretch 10 centimeters. We have springs like that, that's almost 10 newtons per meter. We do experiments on the springs. There's a lab for that. Okay, so there's another situation when you say compress a spring. So let's draw compression. I think that's 1, 2, 3, 4, 5. Okay, so this is x2. So this is our delta x. So ideally, your spring is not really hitting itself yet. If you think about a spring being a coil of a metal wire, and some of the springs, when it's relaxed, it's actually the metal wires touching each other, or at least near touching each other. So there's not much space to compress. But this could be a spring that stretches and compresses equally, such as something that is a spiral type of spring. You can take a piece of paper, just cut it in a spiral, try to stretch it one way and try to stretch it the other way to simulate compressing and stretching equally. So once you have this, you also get the same exact potential energy. It is due to compression or stretching. So you can basically store the same amount of energy if you can, say, compress a spring by 10 centimeters, or if you can stretch that same spring by 10 centimeters, you would basically store the same amount of energy. So say if your kinetic energy in the first situation is 1/2 K. The delta x is just x1 minus x0. It doesn't matter which one minus which one because we're squaring it. And the other situation, EP, potential energy, is 1/2 k x2 minus x0 squared. So if x1 happens to be equal to the opposite of x2, that means you stretch and you compress the same amount, and these two could be equal to each other. So you can compress the spring to store energy, you can stretch the spring to store energy as well. In our projectile launcher, it's compressing, and say in support structures for cars, the struts, they're compressing, right? Other times you're stretching, such as you're stretching a rubber band, trying to say launch it, and so to talk about this, this is, let's say, we call this a spring or elastic potential energy. Let's finish this. Gravitational potential energy. Okay, so for the spring potential energy, there is this definite origin of x0 that depends on the actual spring. The spring has a natural length when nothing is stretching it. So this is different from gravity, which has its origin be basically floating until you choose it, right? So you have to choose basically the origin to be at x0. So when your position is x0 and then minus x0, then you have no potential energy in the spring. So this is something that you cannot change. So let's say can't change origin because I'll just say can't change origin natural lengths, unless you want to change them both, right? So the origin has to be when you pick the natural length. Say if it's right here, this is 0, and you already picked the natural length is going to be x0. Then this x0, the existence of x0 means you've chosen an origin, so that origin has to be the same for measuring the new position of the spring. Thanks.